Our planet is an ocean world. More than 70% of its surface is covered by water. This vast, shimmering expanse holds countless mysteries. We sail its surface, swim in its shallows, and draw sustenance from its bounty. Yet, beneath the waves, an entire universe of phenomena remains largely unexplored. The deep ocean is darker than the darkest night. It has pressures that would crush us instantly. It is, in many ways, more alien than the surface of the moon. We are drawn to its majesty, its power, and its profound secrets. Beyond the creatures that swim and the mountains that rise from the abyss, there are other forces at play. These are invisible forces. They are fields of energy, silent and unseen, yet incredibly powerful. We are talking about electromagnetic fields. These fields permeate the oceans, generated by the Earth itself and by the very movement of its waters. Imagine an invisible network of energy, a hidden dimension shaping the marine environment. This is not science fiction. This is the real, dynamic, electrical nature of our planet's oceans. Humankind has always had a deep connection with the sea. Ancient mariners navigated by the stars, reading the winds and currents. They told tales of krakens and sea serpents, personifying the ocean's might and mystery. Today, our tools are more sophisticated. We have submarines, sonar, and satellites. Yet despite our technological advancements, the ocean continues to surprise us. It challenges our understanding. It reminds us that there is still so much to learn about our own world, especially its vast, interconnected aquatic systems. In this exploration, we will dive into the fascinating world of underwater electromagnetism. We will journey from the basic principles of these fields to the grand concept of a global ocean circuit. We will touch upon mysterious areas like the Bermuda Triangle. We will even ponder whether the seafloor might act like a kind of planetary neural network. Prepare to look at the ocean not just as a body of water, but as a dynamic, electrically charged system, humming with an energy that shapes our world. This journey promises to be quite electrifying. So what exactly are these electromagnetic fields? Think of them as invisible influences, a fundamental force of nature. You experience parts of this force every day. The light you see is an electromagnetic wave. The radio waves that carry your favorite music are electromagnetic. The Earth's magnetic field, which guides a compass needle, is another part. Electricity and magnetism are not separate entities. They are two aspects of the same fundamental force, electromagnetism. One can create the other. It's a cosmic dance. These fields are generated in several ways here on Earth. Deep within our planet, the molten iron core churns. This movement of conductive material creates a massive magnetic field. This is called the geodynamo. It is what gives Earth its north and south magnetic poles. This planetary field extends far out into space, forming the magnetosphere. This magnetosphere shields us from harmful solar radiation. It is a planetary superhero, working silently to protect life on Earth. It's a big deal. The sun also plays a crucial role. Our star is a seething ball of plasma, constantly ejecting charged particles into space. This is the solar wind. When this solar wind buffets Earth's magnetosphere, it causes disturbances. These disturbances can induce electric currents in the upper atmosphere and even in the oceans themselves. Think of it as the sun strumming Earth's magnetic field and the Earth responding with its own electrical song. It's a planetary scale interaction of immense proportions. Electromagnetism is not just an earthly phenomenon, it's universal. It governs the behavior of stars and galaxies. It holds atoms together. Without it, the universe as we know it simply wouldn't exist. Here on our blue planet, these fields are not just curiosities. They are integral to geological processes, atmospheric phenomena, and, as we are about to see, the very nature of our oceans. Understanding them helps us understand the intricate workings of Earth as a complex, interconnected system. It helps us understand our place in the cosmos. Now let's bring this cosmic force down to Earth, into our oceans. Seawater is not pure H2O, it is salty. Those salts, like sodium chloride, common table salt, dissolve into charged particles called ions. These ions make seawater an excellent conductor of electricity. Think of it like a vast liquid wire. Pure water is a poor conductor, but add a little salt, and suddenly it can carry an electrical current quite effectively. Our oceans are brimming with these dissolved salts, making them electrically alive. The oceans are never still. They are in constant motion, driven by winds, temperature differences, and salinity gradients. These movements create massive ocean currents. Some are famous, like the Gulf Stream in the Atlantic, a veritable river within the ocean. These currents transport enormous volumes of water across the globe. They carry heat, nutrients, and, importantly for our discussion, those electrically charged ions. These are not gentle meanders. They are powerful, persistent flows, shaping climates and ecosystems. Here's where things get really interesting. When a conductor, like salty seawater, moves through a magnetic field, an electric current is generated within that conductor. This principle is called motional induction. It's the same basic principle used in power generators to produce electricity. Earth has its own magnetic field, remember? So as these massive ocean currents flow, cutting across Earth's magnetic field lines, they generate electric currents within the seawater itself. The ocean becomes a giant natural generator. These induced electric currents are not trivial. They can be quite significant, flowing over vast distances. And, as a fundamental rule of electromagnetism, wherever there is an electric current, a magnetic field is also created. So the electric currents generated by ocean movements produce their own secondary magnetic fields. These induced magnetic fields can be detected by sensitive instruments. It's a beautiful interplay. Earth's main field causes currents, and those currents create new, smaller fields. The ocean is constantly generating its own electromagnetic weather. The phenomenon of motional induction in seawater isn't just a local effect. It happens all over the globe, wherever ocean currents flow. This leads to the fascinating concept of a global ocean circuit. Imagine the world's oceans as a single, interconnected electrical system. The major ocean gyres, those large rotating current systems, act like giant loops in this circuit. The Earth's magnetic field provides the background influence, and the moving seawater acts as the conductor, generating widespread electrical energy. This global circuit is incredibly complex. The strength and direction of the induced electric currents and magnetic fields vary. They change with the speed and path of the ocean currents. They change with the local strength of Earth's magnetic field. They even change with the conductivity of the seawater, which depends on its temperature and salinity. Scientists use sophisticated models and measurements from ships, buoys, and even satellites to map these oceanic electromagnetic fields. It's like trying to map the weather, but for electricity within the sea. Think of this oceanic electrical grid. It is constantly active, a dynamic system powered by the kinetic energy of ocean currents and the Earth's own magnetism. This circuit is not just confined to the surface waters. Electric currents can also flow deep within the ocean and even interact with the seabed. The Earth's oceans are not just passive bodies of water. They are active participants in the planet's overall electromagnetic environment. This is a profound shift in how we perceive our oceans. The implications of this global ocean circuit are far-reaching. It influences the Earth's total magnetic field as observed from space. It can affect the accuracy of compass readings, especially for highly precise navigation. Understanding this circuit is crucial for interpreting magnetic survey data, which is used for geological mapping and resource exploration. It's another layer of complexity, another testament to the intricate, interconnected systems that make our planet a living, breathing, electrically charged world. It's a planetary-scale electrical engineering project designed by nature itself. Section 5. Whispers from the Deep. The seafloor's electromagnetic signature. You know, the ocean's electromagnetic story doesn't end at the water's surface or even in its deepest currents. The seafloor itself plays a crucial role. The Earth's lithosphere, its rigid outer layer, meets the more fluid asthenosphere in the upper mantle. This boundary beneath the oceans is a site of significant geological and, consequently, electromagnetic activity. The interaction between the conductive seawater, the Earth's main magnetic field, and the geological structures of the seafloor creates a complex electromagnetic environment right at the bottom of the ocean. One important phenomenon is the flow of telluric currents. These are natural electric currents that flow through the Earth's crust and mantle. They are induced by changes in the Earth's external magnetic field, primarily caused by solar activity. When these telluric currents encounter the highly conductive ocean, their behavior changes. The seafloor, with its varying geological composition, from thick sediments to volcanic basalt, influences how these currents flow and how they interact with the overlying seawater's own induced fields. Scientists use a technique called magnetotellurics to study these deep Earth structures. By measuring the natural electric and magnetic fields at the seafloor, they can infer the electrical conductivity of the underlying crust and mantle. This helps them map out features like magma chambers beneath mid-ocean ridges or identify an accumulation of fluids. The seafloor, therefore, is not just a passive boundary. It is an active participant, shaping the electromagnetic fields both within the Earth and in the ocean above. It's like using an electrical probe to see deep inside the Earth. The composition of the seafloor varies greatly. Mid-ocean ridges where new oceanic crust is formed are hot and geologically active. Subduction zones, where one tectonic plate dives beneath another, are sites of intense pressure and temperature changes. These different geological settings have distinct electrical properties. They influence the patterns of induced electric currents and magnetic fields. Studying these variations helps us understand plate tectonics, hydrothermal vent systems, and even the distribution of mineral resources on and beneath the seafloor. The rocks themselves tell an electrical story. Section 6, A Planetary Mind, introducing the seafloor neural network idea. Now let's explore a more speculative but incredibly intriguing idea. Some scientists have proposed that the complex network of electromagnetic fields and currents in the oceans and seafloor might function somewhat like a neural network. This is the concept of the seafloor neural network. It's a powerful analogy. It helps us visualize how information, in the form of electromagnetic signals, might be transmitted and processed across vast oceanic regions. It's a way to think about the ocean's interconnectedness. Think about how a brain works. Neurons or nerve cells transmit electrical and chemical signals. They form intricate pathways, allowing for complex computations and responses. In the ocean, the neurons could be represented by the conductive pathways in seawater and the seafloor. The signals are the electromagnetic fluctuations. These signals can be generated by ocean currents, by interactions with the Earth's magnetic field, or by geological activity. These pathways aren't fixed like wires, but are dynamic and ever-changing. This seafloor neural network wouldn't be conscious, of course. It wouldn't be thinking in the human sense, but it could represent a system capable of transmitting information over long distances. For example, a large geological event, like an undersea earthquake or volcanic eruption, creates significant electromagnetic disturbances. These disturbances could propagate through the oceanic network, potentially detectable far from the source. It suggests a way the Earth system communicates with itself, electrically speaking. The idea is still in its early stages of research. Scientists are working to understand how these signals propagate. They study how different parts of the ocean and seafloor are electromagnetically connected. They are trying to decipher the language of these natural electromagnetic signals. If this concept holds true, it could revolutionize our understanding of Earth system dynamics. It suggests a level of interconnectedness and responsiveness in our planet's oceans that we are only just beginning to appreciate. The Earth might have its own way of feeling its own pulse. Section 7. Mysterious Hotspots, the Bermuda Triangle and Magnetic Anomalies. Certain areas of the ocean are famous, or perhaps infamous, for unusual phenomena. The Bermuda Triangle is a classic example. This region in the western North Atlantic Ocean has long been associated with mysterious disappearances of ships and aircraft. While many of these stories are exaggerated or have conventional explanations, the area does exhibit some interesting geophysical characteristics. It is a region of complex ocean currents and variable weather. And yes, it has notable magnetic features. The Earth's magnetic field is not perfectly uniform. There are regional variations known as magnetic anomalies. In the Bermuda Triangle area, compasses can sometimes show slight deviations from true north due to these local anomalies. These are not usually dramatic enough to cause experienced navigators to become hopelessly lost today. However, combined with sudden, severe storms and the strong currents of the Gulf Stream, such magnetic variations could have contributed to navigational challenges in the past, particularly for less technologically advanced vessels. Beyond the Bermuda Triangle, other oceanic regions exhibit strong or unusual electromagnetic activity. Mid-ocean ridges, where tectonic plates spread apart and magma rises, are hotspots of hydrothermal activity and associated electromagnetic signals. Subduction zones, where one plate grinds beneath another, also generate significant electrical and magnetic disturbances due to friction, fluid release, and rock deformation. These geologically active areas are like noisy junctions in the ocean's electrical grid, constantly buzzing with energy. Studying these strong electromagnetic areas is crucial. They provide natural laboratories for understanding the processes that generate these fields. They can also offer insights into resource formation, such as mineral deposits associated with hydrothermal vents. While the idea of the Bermuda Triangle causing paranormal disappearances is largely myth, the underlying science of magnetic anomalies and strong ocean currents in that region and others is very real and very fascinating. These are places where the Earth's inner workings make themselves more obviously known. Section 8. Life in an Electric World, Marine Biology and Navigational Clues. The ocean's electromagnetic fields are not just an abstract physical phenomenon. They have a very real impact on the life that inhabits the seas. Many marine animals have evolved incredible sensitivities to electric and magnetic fields. Sharks, for instance, possess specialized organs called ampullae of Lorenzini. These gel-filled pores can detect the minute electric fields generated by the muscle contractions of their prey, even when the prey is hidden beneath the sand. It's like having a built-in fish finder. Other creatures, like sea turtles, salmon, and spiny lobsters, are thought to use the Earth's magnetic field for navigation during their long-distance migrations. They seem to possess an internal magnetic compass. How they sense the field is still a subject of intense research. Some theories involve tiny magnetic particles in their cells, or even a quantum mechanical process in their eyes. Imagine navigating thousands of miles across the open ocean using an invisible force. It's an astonishing feat of biological engineering. Human activities are also intertwined with oceanic electromagnetism. Submarines rely on precise knowledge of the Earth's magnetic field for navigation, especially when submerged and unable to use GPS. Anomalies in the magnetic field can be used to detect large metallic objects, like shipwrecks or, in a military context, other submarines. The study of these fields, therefore, has practical applications for both civilian and defense purposes. Our technology must account for these natural fields. Furthermore, understanding the background electromagnetic environment is important as we introduce more of our own electrical and electronic systems into the ocean. Cables for communication and power, offshore wind farms, and various sensor platforms all interact with or generate their own electromagnetic signatures. We need to understand how these might affect marine life or interfere with sensitive measurements. The electric ocean is a busy place, and we are adding our own signals to the mix. We must be mindful of the existing natural symphony. Section 9. Charting the Depths. The Future of Understanding Oceanic Electromagnetism. Our exploration of the ocean's neural network, its vast electromagnetic system, is far from over. In fact, we are just scratching the surface, or perhaps just dipping our toes into these electrifying waters. There is so much more to learn, so many more discoveries waiting to be made. The deep ocean remains one of the last great frontiers on Earth. Its electromagnetic dimension is perhaps the most enigmatic part of that frontier. This field of study is ripe for innovation and breakthroughs. Future research will involve more sophisticated sensors. We'll deploy autonomous underwater vehicles, AUVs, equipped to map electric and magnetic fields with unprecedented detail. We'll use satellite measurements combined with seafloor observatories to get a more complete, three-dimensional picture of these dynamic systems over time. Advanced computer modeling will help us simulate and understand the complex interactions between ocean currents, Earth's magnetic field, seafloor geology, and even solar activity. We are building better tools to see this invisible world. Understanding oceanic electromagnetism has profound implications. It can improve our models of ocean circulation, which are vital for climate prediction. It can help us locate and monitor undersea volcanoes and earthquake zones, potentially improving hazard assessment. It can lead to new methods for exploring for marine resources, and it can deepen our appreciation for the intricate ways marine organisms have adapted to their environment. The knowledge we gain will ripple through many scientific disciplines. The ocean's global electric circuit and the concept of a seafloor neural network challenge us to think about our planet in new ways. They highlight the interconnectedness of Earth's systems. They remind us that even the most familiar parts of our world, like the ocean, hold deep and fascinating secrets. As we continue to chart these unseen forces, we are not just learning about the ocean, we are learning more about the fundamental workings of planet Earth itself. And that, as always, is a journey worth taking. The universe is out there, and a big piece of it is right here in our oceans.